So let's introduce it's available recently. Akihiro Munemasa, the last two lectures.
Thank you. So this is the seventh lecture, and I think at the end of the sixth lecture, I said that I will talk about the splitting field and most importantly, whether the eigenvalues of the adjacent symmetries belong to cyclotomic fields. But I decided to postpone it on to the eighth lecture. So the seventh lecture consists of prime parameter and tensor product of characters, and the most interesting part, and it's the most interesting for me, will come at the eighth part. So at the seventh part, that is this lecture, it is still kind of elementary stuff on representation theory of finite group. So it might be still a bit boring to experts. Okay, so so let us begin with the reviewing material for general commutative association scheme. If association scheme is commutative, we have two bases of the scheme: adjacent symmetries and primitive idempotence, and they are connected by the eigenmatrices. The first eigenmatrix P, which transforms idempotence to adjacent symmetries, and essentially its inverse Q. That's true. I have a mistake here. I have to divide by the size of omega here. So the prime parameter appears when you try to expand the entry-wise product of primitive idempotence into a linear combination of primitive idempotence. So these are called the prime parameters. And in a few lectures ago, I showed that they are non-negative real numbers. And that was a basis for a combinatorial application, because the non-negativity could be used to derive some inequality for combinatorial objects, either the association scheme itself or subsets of association scheme like cliques. Now, the purpose of this lecture is to develop a little more about the representation theory, or rather character theory of finite groups. And at the end, I will mention a result with Scott about which connects prime parameter and tensor product of character. So let me begin with the right regular representation. We already discussed what the central primitive idempotents are, because they come from the center, and we explicitly computed what they are. They are a linear combination of permutation matrices, but the coefficients are a class function called the characters. So for each primitive idempotent, Ej, there is associated irreducible character Ij, and to get the right idempotent, one needs to take the complex conjugate. In general, in the centralized algebra or association scheme, the central primitive idempotents are just the diagonal matrices in the standard block diagonalization. So, but for the right regular representation, we have seen that the size of the matrix is same as multiplicity. So you have this Ej, which is the identity matrix of size mj squared on the diagonal, and the rest 0. So that was the block possessed by the primitive idempotent. Here, this mj is nothing but the value of the character at the identity, which is the dimension of the irreducible representation. And that is repeated mj times. That's why we get this primitive idempotence. And primitive idempotents are orthogonal to each other because from this form it is clear that the positions of at diagonal ones are disjoint. So if you multiply different ij, then you get 0. Another fact coming from this diagonal form is that these idempotents are Hermitian. I think I already mentioned for the general case, but let me recall why this is the case. It's needed because it's just diagonal 0-1 matrix conjugated by a unitary matrix. So this matrix is Hermitian. So Ej is same as Ej star. But then if you compare Ej star, which is same as Ej, using this formula, the taking star means taking complex conjugate and transpose. So you get this complex conjugate disappear, and the transpose of PG is just the inverse, PG inverse, but they have to be the same. So if you compare, well, to be able to compare these two formula, you need to change the variable g to g inverse. Then you get the same expression, different possible, differently looking coefficient. But then the coefficient has to be the same, so this coefficient chi j g bar is equal to chi g inverse. And so this is arbitrary irreducible character. Well, of course, if you are familiar with the representation theory of finite group, and then it is well known that every finite dimensional representation is equivalent to unitary representation, and then this is immediate from that. Okay. From this, one can deduce the well-known orthogonality relation of characters. So, to get that orthogonality relation of characters, let me just compute the product of two primitive idempotents. So, primitive idempotents, we have a formula already on the top line. So, EI, okay, I just have to replace J by I to get the formula for EI. And then EJ, I just copy that formula. But then, how do I multiply these things? Well, I can just collect the coefficients, and then I just have to multiply those permutation matrices. But the permutation matrices PG times PH is just P of GH. So I get this expression. But we know that if I is different from J, then this product is 0. So all the coefficients of a fixed permutation matrix is 0, but it's enough to look at the coefficient of the single permutation matrix, that is the identity matrix. So to get the coefficient of identity matrix, of course, the left-hand side is 0 matrix, so that is 0. What is the coefficient of the identity matrix, P1? Well, then you have to impose the condition that the G has to be H inverse. So really, this is sum becomes sum over H only, and G is replaced by H inverse. And then this conjugate on top of H inverse just disappear because of this property I mentioned, that it is Hermitian. The property that comes from the Hermitian matrix is that this inverse conjugate is just itself. So this is the orthogonality of two different characters. So it looks very much like a Hermitian inner product. you think of the characters, the vectors, and then you have two different vectors, chi I, chi j, indexed by group elements, and one is conjugated, so this is the Hermitian inner product defined on the space of all functions on G. Now, if you do the same for I equal j, then this time you get a non-zero number. But what exactly is that non-zero number? Well, we have the same formula, except that this time I is set to be j, so I'm computing ej squared, which is same as ej. So again, let's look at the coefficient of identity. Coefficient of identity, here again, I have to enforce that the G is equal to H inverse, but of course we did that. The only difference from the previous computation is that the I is equal to J. So I don't have I here, but rather J. And I should compare this with the formula which I have for Ej, because Ej is equal to Ej squared. But I have Ej here, and the coefficient of identity here is, this is chi j 1. I have to take G to be 1, so this is the coefficient of identity in Ej, and on the right hand side I have a coefficient of identity of Ej squared. So I equate them. But then, well, these, the scalar in front are equal, except that I have extra order of G in the new denominator. So what I get is this final formula that if you divide this usual Hermitian inner product by the order of G, you get 1. So if you normalize the usual Hermitian inner product by dividing it by G, you get the orthonormal system of vectors. That is the characters from an orthonormal system. Of what space? Well, it is a space of all functions which are constant on the conjugacy classes. So this is the orthonormality relation we established, and for shorthand notation, I just abbreviate this normalized Hermitian inner product by usual notation for inner product, but I just keep G so that I know where I am taking the sum over. So the chi and psi are complex value function of G. Then their inner product is just a normalized Hermitian inner product. Now this formula I just established in the previous 2 slides just reads that the irreducible characters form an orthonormal basis with respect to this inner product. Well, the basis of all functions which are constant on conjugacy classes. So these are called class functions. And the dimension of the space of class function is precisely the number of conjugacy classes. And we already realized that the number of conjugacy classes is same as the number of irreducible characters. So that's why we do have a complete orthonormal basis. So this is the quite fundamental result in the representation theory of finite group. Okay. Now next let's look at the prime parameter in our setting. Although it's not precisely the prime parameter in the representation theory, but we have defined prime parameter using the entry-wise product of primitive idempotence. So this was the formula for the central primitive idempotence, or the primitive idempotence of the center of the group algebra. That was a adjacency algebra of commutative association scheme. So in the previous computation, I computed EI times EJ or EJ square in the ordinary multiplication. But this time I multiply them by entry-wise multiplication. So EI is copied from EJ, where J is replaced by I, and EJ is just the same. So I multiply these two matrices with respect to the entry-wise product. So what do we get? To compute the entry-wise product, I just have to look at these PG and PH and notice that the two permutation matrices of the regular representation are disjoint if G and H are different. So if I make the entry-wise product, they are almost always 0, and the only exception is that the G is equal to H. So that's why you get just the PG or PH with the same coefficient, just the coefficient-wise multiplication. So that's what you get on the right-hand side. On the other hand, the left-hand side, that is the definition of the prime parameter. So EI circle EJ, the entry-wise product, is expanded in terms of central primitive idempotency K with coefficient given by prime parameters. Well, to get a single prime parameter or single summand on the left-hand side, I just have to kill all but one EK, but that is quite easy because the idempotents are pairwise orthogonal. I can just multiply single EK on both sides to kill all the summand except one. So I get this formula. So this gives the expression for Qijk times primitive idempotent Ek. Well, I don't give you the detail, but here you still have to compute using the formula that this Ek can be written in this place. So you have to multiply those permutation matrices with these permutation matrices, but we have shown how to do that. So you just repeat that process to get the formula for the prime parameter. Again, you can look at a particular entry of both sides and to get this formula for Qijk. Then, well, it's after certain simplification, you get this formula Qijk written in terms of inner product of 3 characters, Chi-I, Chi-J, and Chi-K. Yeah. So this is the sum of all group elements H of the character values, because Chi-I, Chi-J appear here, and this Ek gives this Chi-K from upstairs, so you get this formula for Qijk. So from this, the prime parameter in this special case is nothing really new. In character theory of finite groups, this kind of coefficient is quite important. It is called the tensor product coefficients. I will explain why they are called tensor product. So the Qijk differs from tensor product coefficients only up to this scale, which is just a positive rational number. Okay, so what are the tensor product coefficients? So this inner product of 3 characters, Chi-I, Chi-J, comma Chi-K. This is called the tensor product coefficient because of the following reason. Yeah, there is a tensor product representation. Because if you recall what the character was just a trace of a representation. So character is associated to a representation which I wrote phi before. Phi is a homomorphism from the group G to general linear group, say, of size mi, and the trace is denoted by chi I, and that is called the irreducible character. Then what is the product of characters? Well, the product of trace is not trace of the product. Rather, the product of trace, chi I G, chi J G, that's the product of trace, is trace of the bigger matrix that is called the Kronecker product or tensor product. And you may think of this phi G tensor phi J G as a big matrix, and associating this big matrix to each element of G is another homomorphism, so it is a representation of G. So whenever you are given two representations, phi I and phi J, then the Kronecker product or tensor product is another representation. And the dimension is just the product of these two. And so this is called the tensor product representation, and the trace of that representation is just the product of each of the trace. So this is why the chi I times chi j is the tensor product of characters. Now, then what is the meaning of this coefficient? The coefficient, the value of the inner product turns out to be a positive integer. And if I denote by m, then it gives the multiplicity of the irreducible representation chi k of inside this big representation. You know, phi I, phi j is a representation, phi I tensor phi j is a representation. If you consider the image, then it is, the algebra is again the star algebra, so you can block diagonalize it. And after block diagonalization, you get deep block decomposition, and you can count, well, some of them are isomorphic to this particular representation of phi k. So suppose it is repeated m times, and that m can be computed by just looking at the character value. That is the inner product. So that is why this inner product is called the tensor product. So we have very well understanding of the Klein parameter for this particular association scheme. But in general, we don't have such a nice interpretation. Well, Klein parameter can be defined for any commutative association scheme because we have primitive idempotence. That's how we expand the entry byproduct of primitive idempotence. But then what are the Klein parameters? Do we have some meaning like tensor product coefficients? Well, we could try to see what will happen by using the same kind of formula. Instead of the formula of central primitive idempotence in the group algebra, we do have the formula due to Curtis and Fossum that gives primitive idempotence in terms of adjacency matrices. Of course, we do have such a formula here, but the actual entries are given in terms of characters. It's abstractly true that they are the basis, so there are some coefficients expressing Ej in terms of AI, but the coefficients are explicitly computed using using this formula, and it's written in terms of characters. So from this formula, or more abstract theory, you see that the primitive idempotence, they are indexed by J, and also this index appears in this particular place, that is the irreducible character. I think I already explained that because the algebra of representation is a homomorphic image of the group algebra, so you do get the partial correspondence between the central primitive idempotence of the group algebra and the primitive idempotence of the central algebra. Well, it is not one-to-one correspondence because the centralizer of a permutation representation could be smaller, so you might lose some central idempotence of the group algebra, but you just index in such a way that the first, say, the R of them are same as the first R of the those primitive idempotents in the center of the group algebra precisely corresponds to those appearing in the centralizer. So the point is that the indices of these crime parameters, the IJK, which appear in the expansion, are same as the indices appearing in the primitive idempotents, which are part of the indices of the irreducible characters. So it's natural to expect some relation between crime parameters and irreducible characters. Well, that is partially explained by a theorem due to Leonard-Scott. For transitive action, we have that formula for central primitive idempotence. In fact, for multiplicity. So Scott proved this theorem that relates non-zeroness of these two numbers. That it's Qijk, that is the prime parameter, that is the coefficient appearing in the expansion of the entry-wise product of primitive idempotence. This is non-zero implies that this tensor product coefficient isn't zero. I was hoping to give a very rigorous proof of that, but somehow my time is limited, and I'm not sure if I could explain in a very detailed, in an intuitively understandable way. So I just give you a sketch of the proof here in just 3 lines. So this sketch of the proof here is that to get the conclusion, you need to show that this the irreducible representation, the K irreducible representation, that is, which I denote by phi k appeared in this tensor product Pi Pj. So the representation Phi is realized by this idempotent Ei. So let us call Vi. Because Vi is the multiplicity case, so this is just an irreducible module. And the same is true for Pj. So the character Chi j is the character of the representation realized by this tensor product. But the Vi is just an image of the standard module under Ei. So this is nothing but the column space of the matrix Ei. And Vj is also nothing but the column space of Vj. So Vi times Dj is really a Vi tensor Vj is well, you might think that why you get containment, not equality. This is the set of all tensors which are obtained by taking arbitrary elements of this and arbitrary element of this, but you don't have to take arbitrary element, you just take a generator, which are columns of Ei. This little e alpha is for me, the unit vector, standard basis vector of the space C omega. So this means that I have an EI, and E alpha is a standard unit vector. So the product is that this alpha column of the identity, this is matrix EI. So to get the full tensor product Vi tensor Vj, I need to take arbitrary pair of vectors, but instead of taking arbitrary pair of vectors, I take arbitrary columns of the matrix. So I take arbitrary column, alpha column, then I need to take also another arbitrary column of the second space, so I take Ej. But I can't specify the same column. It should be arbitrary column, so I take something else data. So I collect them for all alpha and beta from the set omega. Then, so this will be the generator of this tensor product. So if I take a span, that's what this tensor product is. Well, if you're not familiar with tensor product, you may think of this as a space of matrices. EI alpha, EI times EI alpha, this is a column vector. In fact, the column of the matrix EI. And you may think of tensor product as a column vector times row vector. That is Ej, E alpha, transpose. So this could be sort of just a square matrix. You see, column vector times row vector is a square matrix. So this is what the Vi tensor Vj is. Then here in the first line or the second line, I restrict myself to a special kind of vector Ei, E alpha times Ej, E alpha. So I don't let alpha and beta vary arbitrarily, but I specify alpha and beta to be equal. So that's why I have a subspace. In other words, it's essentially the same as taking some kind of diagonal part of that square matrix. So this is subspace, and it is easy to see the invariant under the group action. And also another thing one needs to check is that if you map this particular vector to this particular vector, then it is a well-defined homomorphism of the linear space, and in fact it is also compatible with the group action. You see, it's not so obvious because these vectors are not linearly independent. So you cannot simply send this to them and without checking well-definedness. So it's a little work is involved to show that there is homomorphic linear mapping which sends this to that. But once you see that there's a linear mapping, it's clear that this is compatible with the G action, and because of this EK, this is a subspace of VK, that is EK times the standard module. And this subspace is non-zero precisely when the crime parameter is non-zero. So the crime parameter is non-zero, then you have a non-trivial homomorphism which is compatible with G action. So it means that you have a copy of VK, I mean isomorphic copy of VK, because VK is irreducible, found in Vi tensor VK. So that is why this VK lives in this tensor product. So the tensor product coefficient which gives the multiplicity is non-zero. So once you understand these two-line formula, the proof isn't so difficult. But I still don't feel that I have a complete understanding of the situation because, well, big main reason is that I don't quite understand the difference between these two. This containment, and don't quite understand this space either. And the main difficulty is to understand the coefficient. Well, the coefficient doesn't really have a combinatorial meaning because it's just a scalar which maps some part of the irreducible module to the other. So, but the importance is whether this is non-zero. But the point is that because of this containment, you're not considering the whole tensor product, but part of the center tensor product. So that is why you only get one-sided implication. The proof comes only from this part of the tensor product module to VK. So you can't reverse the implication because this is non-zero if VK lies in this, but the VK might lie in VI tensor VJ but not here. Then it may have no connection to prime parameter. So this is not so difficult theorem, but I feel still that our understanding of the situation is somewhat unsatisfactory. So if you're interested in, you might want to ask the student Keiji Ito, who proved the converse of the theorem under certain special case. Okay, so this is what I'm going to talk about in the next lecture, that is the final lecture. I promised that I will do that in this lecture, but I decided to postpone it to the next one. So for the transitive action, we have the formula to Curtis and Foster about the primitive idempotence. We have seen this formula over and over. So you kind of know what these are, central primitive idempotence. And the end of the sixth lecture, I mentioned that the characters of the finite group, that is the value ijg, they are cyclotomic numbers, that is, they are sum of roots of unity. So they belong to certain field extension obtained by adjoining root of unity. So in this case, L is the root, L's root of unity, and it is sufficient to take L to be the exponent of G. So this number belongs to this field, and you can compute the trace of Ej times Ai by multiplying Ai from the right, and then computing the trace, but then the only non-rational thing which might occur is this one. So from that you see this number is also cyclotomic number belonging to this field. Or more explicitly, if you notice that the trace of Ai times Aj is almost always zero, except that Aj is transpose of Ai, then the multiplying Ai from the right kills almost all terms except the single one. So computing this really gives very simple formula. So really the eigenvalue of the adjacency metric is this sum of all these character values divided by the order of h. So definitely this is a sum of roots of unity. But this argument works only when when we have this formula, that is only when we have finite group, characters of finite group, and it doesn't work if we don't have a finite group. So, so the open problem stated in the book by Akihiro is that can we say something similar for commutative association scheme without assuming any group action? Well, if we do not assume group action, we have, as long as the scheme is commutative, we have adjacent symmetrices and primitive idempotence. So we have this expression, and these coefficients are nothing but the eigenvalues because Ej are idempotents. So eigenvalues are nothing but the entry of the so-called the first eigenmatrix, that is the matrix P used to express adjacent symmetrices in terms of primitive idempotence. So the open problem stated in Akihiro is that the given commutative association scheme R are the entries of P. Those are the eigenvalues of adjacent symmetries belong to, I should do the entries or belong to the cyclotonically. That's the question. And yes, for group case, that is, if the association scheme come from the group action that is multiplicity free, then we have the formula, and we see in the previous slide they do belong to the they do belong to the cyclotomic field. Okay, so that's all for the first lecture. I will try to prove part of the program by assuming that the crime parameters are rational. Okay, thank you for listening.
Thank you. So would there be any question or comments?
Yeah, then if I may say, I mean, for me, it appears that Scott's theorem is sort of general. I don't know. I think it's more or less obvious. Because if you have, if the crime parameter is not zero, you have a bilinear mapping I, E, J to EK, and then obviously the tensor product coefficient should be not zero. Well, the reverse is much harder. It's probably not true. Yeah. Okay. Any more questions? If not, we have a break and resume at 11 o'clock.